So that's horizontal circular motion stuff. We're going to move on to vertical circular motion stuff now. So we'll talk about horizontal motion actually. So centripetal force is net force. Okay, centripetal force and net force are the same thing, except centripetal force is only talking about the forces directed towards the center of the circle. Any forces that are perpendicular to the center of the circle are not included in our FC equation, right? So these are two different views that you can look at something moving in a horizontal circle. So this is a side view, and this is a top view, right? If this is a ball and this is a string, then our force of tension goes towards the center of the circle, right? That's all we could really see in the top view. The side view, it's our force of tension that goes towards the center of the circle. But if we draw on gravity in the side view, well, our force of gravity would go that way. And I guess, no, there is nothing there because it's not sitting on a surface. So we have a force of gravity downwards, right? We don't include gravity in our FC equation because it's not going towards the center of the circle. We only want to include things that go away or towards the center of the circle. So if I wrote an FC equation for this, I would write FC equals FT. It's kind of like when we had an object. So we have FG here, we have FT here, and force normal here, and then a force applied this way. If I wrote an F-net equation for this, for the direction of the motion, right, I would say that F-net is equal to FA because these guys cancel out, so I don't include them because they're not in the direction of the motion. Well, it's the same idea. Instead of writing an F-net equation, we write an FC equation, same idea, but I only want to include things that go away or towards from the center of the circle. Okay. So you'll notice that with this, we have our force of tension towards the center of the circle, our force of gravity down. If I tipped tail, add those. So this is my force of tension, this is my force of gravity, and this is my net force acting on it. You can see that my net force is at an angle here, and that's what you see with the swing of century, right? The faster these move, the more they go upwards because we get a bigger force of tension, and the slower it's moving, the more you have in this force of gravity. And that's why they are at an angle there. And this would be about the time we would be going to Galaxyland, but we can't now. So sorry, that would have been fun. Vertical motion. So when an object is going in a vertical circle, there are two positions where gravity is parallel to the direction of the center of the circle. So these are a vertical circle. These are all side views, right? So let me switch to my camera. When we're talking a horizontal circle, we're talking about something spinning like this. When we're doing a vertical circle, we're talking about something spinning like this, right? Upwards like that. That's a vertical circle. So these are all side views here. So think of this as like a loop-to-loop on a roller coaster. So but I'm swinging a string. So with all these situations, the string is what makes it move in a circle. So the force of tension is always towards the center of the circle. That's how strings work. They keep it going in a circle, so the force of tension is always towards the center of the circle. But if we draw on gravity, gravity's downwards. So we have Fg downwards, Fg downwards, Fg downwards, and Fg downwards. So two of these situations, you have gravity that's perpendicular. So this situation, they're perpendicular. This situation, they're perpendicular. We wouldn't include gravity in our FC equation. But because it's parallel to the center of the circle, we would include gravity in our FC equation for these two situations. Okay, so when gravity is included in the FC equation, it can affect the weight of a person riding in a vertical circle. So we have to remember that Ft is equal to our apparent weight. We did this in elevator questions. And that the positive values are always forces that are directed towards the center of the circle. So this is important. So if I just draw on, so Ft is up, or Ft is towards the center of the circle, and then Fg is down. It's too far down. It won't let me go that far. There we go. Fg is downwards, right? And then in this situation, because Ft is always towards the center of the circle and Fg is down, they're in the same direction. So if I wrote an FC equation for this, so remember that positive values are always directed towards the center of the circle. That's that's what we're going to use. So this is positive, this is negative. They're going in opposite directions, so I'd say positive Ft and negative force of gravity. That's what my FC equation for this would look like. Both of these are going towards the center of the circle. So if I wrote an FC equation for this, it would be Ft plus Fg, and that's what my FC equation works. And this is actually easier than what we've been doing before in our first couple of units, because this is what the FC equations are always going to be. With FNet equations, you could have a million different things, but with this one, this is what it's going to be. So let's do an example. A 75 kilogram man rides a roller coaster with a vertical loop of a radius 5 meters. The radar gun clocks the roller coaster at a constant speed of 7.25 meters per second around the loop. Sketch a free body diagram of the roller coaster at the top of the loop. So gravity's easy. Gravity's downwards. And the other force acting on this is weird. If you think of what the other force would be, well, what would it be? We have force of gravity, we have force of tension, force applied. None of those really fit. What it actually is it's force normal. And force normal is always opposite of the surface. So the other force acting on this is a force normal downwards. But that can be a little bit confusing. So what you can do for all these questions is if you just picture a string is attached to this, the physics would be exactly the same. And it's a lot easier to picture something being swung around, swung around in a circle like this, and having a string attached to it and drawing out the free body diagram. And you can always use that. So sometimes instead of force normal, I call it force tension, even though there's no string attached to it, but just to keep it consistent. Okay. So if I write an FC equation, because everything's going to the center of the circle, it's positive. So I'm going to say FC is equal to force of tension plus force of gravity. Remember that it's actually force normal, but I'm just going to call it force of tension to keep it consistent. What is the apparent weight of the man if he stands on a Newton scale while going upside down on a roller coaster? So this is our apparent weight. And this is our normal weight. Right? So we have apparent weight and we have a normal weight, and we want to find the man's apparent weight. So let's do this question. Okay, so we start off with our FC equation, much like an FNet equation. And because they give us a speed, we can break this down into mv squared over r. Right? Force of tension is what we're trying to find. That's our apparent weight. And this I can break down into mg. So if I'm trying to find force of tension, I have mv squared over r. I have to subtract an mg from both sides, and that would give me force of tension. So the man is 75 kilograms. The speed is 7.25 meters per second, and I have to square it, and my radius is 5 meters. And then I subtract 75 kilograms times 9.81 meters per second squared. So that's going to be my calculation. Oops. Oops. Come on. There we go. So I would go 75 times 7.25. Oops. I should double bracket this to start. So I'll close the bracket for the top stuff, and then I'll divide it by 5, and then close my bracket for the bottom stuff, and then I'm going to subtract 75 times 9.81. forgot to square it's mv squared. I forgot to square that. Oopsies. Let me throw a squared in there. Oops. There we go. mv squared. And that gives me a much more reasonable answer. So the weight is 52.7 newtons, right? And we can find their normal weight. Their normal weight is just going to be mg, so 75 times 9.81. So this is their normal weight. This is their apparent weight. Well, they're going to feel a lot lighter, and they're going to get that butterfly feeling on their stomach while doing this loop-to-loop on this roller coaster. Okay, so we can do the same thing at the bottom. So at the bottom, gravity is downwards. And if we picture a string being attached to this, our force of tension is always towards the center. So we end up getting Fc equals positive force of tension and negative force of gravity because it's away from the center of the circle. So our equation would be super similar. The only difference is this ends up being negative, right? So if it's negative over here, then we'd have to add an mg. So the only difference is it's going to be a positive. Same mass, same speed, same radius, same mass, same acceleration, but it's just going to be positive. So if I go back to the exact same thing that I just typed in, and I push second enter, right, the only thing that's changing is this negative is going to become a positive. This is their normal weight. This is their apparent weight at the bottom of the loop. So at the bottom of the loop, they feel heavier. And at the bottom of the loop, you will always feel heavier because whenever we find out our apparent weight, we always end up adding those two numbers together. Okay, that's important, and we'll do some practice questions with that tomorrow. So let's do a board question. Or, no, we need to do, sorry, I missed a question here. Okay. So to do this next question, I have to open this simulation here. Where we can have a skate park, and we've seen this before in energy. I don't know if I showed you in energy, I don't know what's going on, but we have a loop here, and let's switch to the bulldog because it's way better. There we go. So we got a bulldog. So in the question it says, what will happen if a 20-kilogram bulldog starts from a height of 7 meters? So we're going to start from a height of 7 meters. There we go, close enough. So he starts from a height of 7 meters. Let's pause it, get out of here. Okay, so we're starting from a height of 7 meters. And how fast will he be going at the top of a 2-meter radius loop? So if it's a 2-meter radius loop, the diameter is 4 meters. So I'm just going to measure out 4 meters here. There we go. So we have oh, that's a little bit bigger than 4 meters. Try to make it as circular as possible. There we go. So there's our 4-meter loop. We're starting from a height of 7 meters. Good. What will his apparent weight be at the top of the loop? Okay. So let's take a look at this equation here. So this is my loop. I guess it goes up again. So this is 7 meters. And this is, let me draw this a little bit better. There we go. This is 4 meters. like that, and this is our bulldog up here. So at the top of the loop here, it's going to be the same as that other situation. Our force of gravity is going to be down, and our force of tension is down as well. So our free body diagram at the top of the loop will be force of gravity down, force of tension down, or towards the center of the circle. So this is going to be Fc is equal to Ft plus Fg, because they're both in the same direction at the top of the loop. Okay, that's really messy. There we go, that's a little bit better. So we want to find his apparent weight. So we want to find this again. So we have mv squared over r equals force of tension plus mg. So I subtract mg from both sides, and I end up getting mv squared over r minus mg is equal to ft. Okay. So we know the mass of the bulldog, we know the radius, we know g, but we don't know the speed. But we can figure out the speed using our physics principle number 5. Right? Remember, with our law of conservation of energy, our energy before equals our energy after. Up here, we have potential energy, right? And then here, we're moving, so we have potential and we have kinetic. But if we move our reference point to here, then we get rid of the potential. This is 3 meters above our reference point, and we just have potential turning into kinetic. So EP is equal to EK. mgh equals 1/2 mv squared. Our masses cancel out. The 2 goes up top, and it's square rooted. So square root 2gh is equal to v. So 2 times 9.81 times our height. It's 3 meters above our reference point. We square root it. We end up getting 2 times 9.81 times 3, square rooted, 7.67 meters per second. I'll use that full answer. So that's how fast we're going. So now we know everything that we need to find our apparent weight. So I'll plug this in. So we have a 20 kilogram dog. We have 7.67 meters per second. Don't forget to square it this time, myself. And then our radius is 2 meters. It's a 4 in diameter and 2 in radius. And then I subtract my 20 kilograms times 9.81 meters per second squared. So when I plug all that in, okay, let's try this again. So I'll go 20 times my answer from before squared divided by 2. It's going to add a bracket. And then we subtract 20 times 9.81. And we get the dog's apparent weight to be 392 newtons. Cool. Why did we do that again? We kind of just did that before. Well, I will show you. So let's take a look. So my next question is, do you think the dog is going to make the loop? Well, let's check it out. Oops. Let's put them right away. So you can see that the dog easily makes the loop. Oh no. So the dog easily makes the loop in this situation. So we're going to make a little bit of a change. So what we're going to do, so what will his apparent weight be at the top? Will he make the loop? And what if the radius is increased to 3 meters? So I'm going to take this simulation, and if the radius is 3 meters, then my diameter is 6. So I'm going to make it a whole lot bigger. That's pretty good. So this is 6 meters. Yeah. And do we think he's going to make the loop this time? Well, let's take a look. So if we go back to our equation and we think about, well, what's going to change if we make it 6? So all we're changing is making this loop bigger. So it's now 6 meters. Well, our speed is going to be different, right? Because if we want to measure our reference point, it's going to be from the top of the 6 meters. So we're only going to be 1 meter above our reference point to start. So if I go through this equation here, well, that's only going to be 1 meter. So I'm going to find a new speed. So if I go 2 times 9.81 times 1, and I square root that, well, I'll be going a little bit slower this time. I'll be going 4.429 meters per second. So that means that this will change. In this equation here, the mass stays the same. The radius is different. It's now a 3 meter radius. And these guys stay the same. So almost everything's the same. So if I go back to that last equation that I typed in, so my radius is now, my radius is now 3. And my speed is now that. Well, we get an answer of, for the second one, we get an answer of negative 65.4 newtons. So what does this negative mean? Well, when we take a look at what the dog does, is he going to make the loop this time? No, right? He flies off. So this would not be good if you were developing a roller coaster, right? If no one could ever make the loop. So that's not good. And that's what that negative means. So if you ever have ft equaling negative something, it means you're not going to make the loop. And this is important because what we'll find out is that, well, what's the smallest ft that you can have? Well, it can be 0, right? And it all has to do with the speed that you have at the top of the loop. So if you have your minimum possible speed, then this ft is going to equal 0. So that's going to cancel out. And you get fc is equal to fg. That's when you're going your minimum speed. Okay, so let's do a board question that shows that. So you are swinging a 1 meter string with a 10-gram eraser circling vertically. What is the minimum speed? Minimum speed, very important. You could spin the eraser at the top of the circle. Okay. So let's do this question. Oh, sorry, I didn't even put the question up. Sorry. Now you can read the question. You're swinging a 1 meter string with a 10-gram eraser circling vertically. What is the minimum speed that you could spin the eraser at the top of the circle? Okay, let's do this. So at the top, so this is a circle, this is a string, this is your eraser. So the length of the string is actually your radius. So at the top of the circle, just like every other time, your force of tension and your force of gravity are both towards the center of the circle. Man, I'm sucking it, putting it on the right camera. So force of tension, force of gravity, same as always, right? So our Fc is equal to Ft plus Fg. But if it's talking about the minimum speed means that this is equal to 0. So if we're talking about the minimum speed, Fc is equal to Fg. This is mv squared over r. This is mg. We move r up top, move mass down below, and you can see those two masses cancel out and square root. So our v is just equal to square root gr. So if I just go 9.81 times 1 and square root it, I get 3.13 meters per second. That's the minimum speed that I can spin that in a circle. And if I go any less than that, then it's not going to make the loop. It's going to fall down like the bulldog did. Okay. This last question here is just a special type of situation. So you're traveling in your car at a speed of 60 kilometers an hour as you go over a hill. Your hill has a curvature of 60 meters and your mass is 60 kilograms. What is your apparent weight as you go over the hill? So if we're going over a hill, our forces look just a little bit different. Okay, so this is me going over a hill. This is me in my car. right here. Let's give myself a little bit more room, like that. So the first thing I get people to do with this is if you were in class right now, I'd get you to draw a free body diagram. So pause the video and try to draw a free body diagram for the forces acting on this as it goes over the hill. Okay. So you have a force of gravity downwards. And the question you need to ask yourself is, well, there's a force normal upwards, but is it bigger, smaller, or the same size? So if you do it bigger, like that, if you do a bigger arrow, what that means is we have a net force upwards. So as this car goes through the circle, it'll go like that. So it can't be bigger. If it's the same size, it's a force normal. If it's the same size, what's going to happen is we have no net force, and then the car will continue on a straight path like that. So that means you'll get some air. That's not good. If we want our car to follow the path of the circle, we need our net force to be towards the center of the circle. So our net force needs to be downwards. So that means that our force normal is actually smaller than our force of gravity. And as always, we can call this force of tension just to keep things consistent. But it is force normal, but we can call it force of tension. This is towards the center of the circle, so it's positive. This is away, so it's negative. So our FC equation is going to be Fg minus my force of tension, right? And this is my apparent weight. This is what I'm trying to find. So I could subtract Fg from both sides. So I get Fc minus Fg equals negative force of tension. And to get rid of the negative, I switch the signs of everything. So negative mv squared over r plus mg is going to be equal to our apparent weight. So everything's 60 here, so it's a 60 kilogram object. I have to make that negative. My speed is 60 kilometers an hour. Ooh, it can't be 60 kilometers an hour because I need to be in meters per second. So I have to make that conversion. There's 1,000 meters in 1 kilometer. And there's hours into seconds, or 3,600 seconds in 1 hour. So hours cancel out. So 60 times 1,000 times 3,600. Oops. So we get 16.6 as our speed. So 16.6 repeated is our speed in meters per second, what we need. Okay, now we're ready to plug stuff in. So negative 60, our speed is 16.6 repeated meters per second. We have to square that. Our radius is 60 meters. And then we add on 60 kilograms times 9.81 meters per second squared. So remember to make this first one negative. So 16 squared times negative 60 divided by 60 plus 60 times 9.81. And we end up getting 310 newtons. So that's the apparent weight. And I find it always helpful if you compare it to their normal weight. So if I just go 60 times 9.81, that's 588.6 newtons. So they feel lighter when they're going over the hill. And that's why you go over the hill at a fast speed, because you do feel lighter. And if you increase the speed, you increase the negative number, so you make that smaller. So the faster you go over, the lighter you feel, and the more butterflies you get in your stomach as you go over the hill. So that's why you'd want to go fast over the top of a hill like that. Okay. Those are the questions. They're all really similar in the homework. This is a homework. It's not very many. 1, 2, 3, 4, 5, 6, 7 questions. Give those a go. If you have any trouble, let me know and I can help you.